All right. So welcome everyone. I guess without further ado, Matt Arsenault.
All right. Hello. So do you want to just like hop in? Because I know this is a bit more informal now, but I can sort of like discuss a little bit about who you are and stuff. All right. So Matt graduated from the graduate program in 2016. And his job title is an assistant director of engineering at CW Keller and Associates. Do you want to sort of talk about like or I guess more of like your job title at CW Keller too?
Yeah, sure, absolutely. So I, so I work at this company called CW Keller, which I'm sure not many of you probably know unless you're some of the students that are in my studio. But CW Keller is an architectural fabrication office that's located in Plastow, New Hampshire. And then we also have a facility in Longmont, Colorado, as well as another location in San Francisco. We have a third remote office. But we do complex architectural fabrication, specifically in the medium of wood, as well as concrete. And we do a lot of design assist contracts where we do direct engineering and working with architects and designers and artists and sculptors to kind of bring the complex ideas and designs to physical reality. Because there's so many, I think now in the contemporary era, especially with the use of kind of digital tools at such our disposal now, that like anything can be designed, but not many people can understand the complexity to build them and figure them out. So that's what my office does. And then my role specifically with the organization is kind of a leader in the engineering team, and I lead project workflows and development, as well as being a member of the internal research and development team looking at new construction technology. And what I do is I lead detail development, project workflow, and then delivery through the engineering to direct fabrication process, as well as the installation of all of our complex projects as well, kind of overseeing it with both our shop team as well as our project management team.
Interesting. So I think it's interesting that you guys are kind of like the people who bring to life all of our like the architects' ideas. Do you mind elaborating a little bit more on that? Like, how do you work with other architects or other engineers on creating these things?
Yeah, absolutely. So we kind of work hand in hand. One of the reasons I was so drawn to the office that I work in particular, is because we're not afraid of any challenge. I think that's something that's really important now, kind of especially in the design world, because designers can be fearless in the way that they create things, but now we need to be fearless in the way that we build things. And that's what my office, kind of a motto that we've had, is to really look at any challenge and not back away from it. And it's working hand in hand with architects or designers or sculptors to work and get them to understand the material aspect of it first, to understand, how to detail something. What's the best way to detail something towards a materiality, towards a process or a procedure for fabrication. And it's really not about, we like to have anybody come to us and say, like, this is our idea. And we never want to turn them away and say, like, you can't do that. Instead, we're going to help them refine, and it's working directly in the process. We do it through model. So our office is exclusively model driven, kind of in the BIM era. So we will work and model directly in Rhino, Grasshopper, and then send models back and forth to clients. And that's how we kind of communicate, is through that space versus a traditional paper space or kind of sketching. That's not to say that our office environment is also extremely collaborative in that way. So it's a very interdisciplinary idea to bring all of these ideas to life.
I think Sam mentioned that you have like some slides set up. Do you want to start going through those, and then we can open up the discussion to everyone else?
Yeah, absolutely. So to kind of give a little bit of background on some of the projects that I've worked on so I've been with CW Keller for 5 years. So I've prepared kind of a presentation of some of the projects that I've worked on over the past few years. And I'm going to focus primarily on one project in particular, which is the project that really brought me kind of to the office, and it's kind of lived with me for a couple of years now. And then to start to really talk about this idea of craft and what this means in the digital era. And this project is going to be the Alliance Theater designed by Trahan Architects, which recently won a Design Award for the best interior architecture for 2020. So this is kind of CW Color. These are a couple small images of projects that our office has worked on. Again, like I previously stated, we do the primary use of all of our medium is going to be woodworking, as well as we work with concrete of doing complex form systems for concrete projects that are highly geometric. This first project I'm going to show is called the 6th Street Viaduct Bridge, which is currently under construction in Los Angeles. It was designed by Michael Maltzen Architecture. The general contractor was Skanska Civil. This project has been under construction for about 12 years right now. It's about 1.5 miles long bridge running right through the center of Los Angeles. It's all concrete systems. You can see the main elements are the swooping arches that are at the top, as well as the Y bends for how it kind of connects to the ground. But the bridge is a pedestrian pathway that shares itself along with being a main throughway for the city of Los Angeles. My office was contracted to actually create a parametric model of the entire bridge system to check in the BIM world to make sure everything lined up. The complexities of the geometries you can see are pretty intense. So we created a full data-driven model that was completely designed only through Excel tables and data points that you could check the alignment of every single one of these parts. So this is a traditional drawing that would come from the engineering firm for this project. And it's basically a diagrammatic drawing of how all of the Y bends in this case are created. And they're just a series of coordinates. So we would input all of these data tables into Grasshopper using an Excel program that would kind of filter out the data. And it would have the ability using kind of planes and points to create each one of the Y bend forms. Each one of these is always unique throughout the entire project based off of the load capacities, as well as kind of its orientation in space, since this bridge is kind of curving through the community as well as changing in elevation. So each one of these parts created a different portion to kind of the center of the Y bend, and then creating the tangent geometry out towards the arms. And what you can see in the bottom image is the green and the red. That's the intended design, is what's in green for the geometry coming from the architecture firm. What's in red is actually the output of data from the data tables and the contract documents. So you can see that they're off in areas almost by feet. There were areas where when we were doing the analysis of this geometry, that one of the arches was off by about 400 feet from being able to hit one of the Y bend geometries. As you know, you can imagine if you're a team in the field, that's a huge problem. So we're able to catch this ahead of time. This was the first project to ever utilize BIM construction for Caltrans, which is the California Association for Transportation, and has now become a global standard for their practice that now every project they do, and they're the first adopted state to make this a mandate for national transportation, to do this on every one of their projects. So our office would model every single piece of geometry. We would also model every single piece of rebar that was embedded inside of it, as well as the plumbing, the ducts on top of the deck system, as well as even putting in the post-tension systems to understand the timeline progression of construction in the form of once they were laying these kind of duct systems through, and then actually tensioning the systems to their final state once the concrete was cured, which is a pretty standard practice in bridge construction. And here's an image of one of the Y bends being constructed. I believe this is one of the 13 Y bends on the north side of the bridge. This was an image from July of this year. And to date, they've poured about half of the Y bends, and I believe they still have about 3 years of construction left until the bridge finally opens. So this is just an example of a type of project my office works in. And that I'm really interested in these ideas of craft about how you can use automation tools to kind of recreate and construct geometry in a real-time data table for how you can visualize and see everything coming together prior to getting to site. The models that we developed were done about 2.5 years prior to the initiation of construction. That could be used for form systems, that could also be used for rebar tables. They could export the data for how long each piece of rebar needed to be, how high the shoring systems needed to be to hold up the form for the concrete, as well as calculate the amount of like volume of actual concrete that needed to be delivered to site, all based off of the data that's driven directly from the model. This next project is another one currently under construction. It's called Woodley Road, or the Montecito residence. It's designed by Shubin Donaldson. This project was really meant to be kind of embedded in coming out of the ground. It's embedded into the hillside and completely crafted. The house overall is about 35,000 square feet. It's massive. It's being designed as a private residency currently, and then it will be used and donated to the city of Montecito, California, to be an art museum and a place for the public to kind of enjoy and overlook the hillscapes of the city and kind of embed themselves underneath. So the whole thing is a cast in place concrete system with some really complex shapes. What you're looking at right now is a courtyard in the center of the building that's referred to as the center avocado. It's very fitting for California to be doing that, but you can see the scale of these spaces of being able to fit cars inside of them. One of them, is basically a garage that could hold 40 cars as just one living space. In these massive vaulting forms with double curvature that are sweeping through. So our office was contracted to do all of the form systems for all of the areas that are curved or double curvature. So we worked with the architect directly to design the form layouts, to design the seam layouts for the way that the aesthetic of the concrete would be once the forms were removed. They all have a wood texture, which we work very heavily with them. And the concrete also brings itself into the interior to create this real cavernous appearance, and then obviously integrating itself with the landscape at the exterior. So these are some images from the design team of this and kind of programmatic use and formation of the building. This is a drawing that breaks down the individual segments. So what you're seeing in this screen here, all the individual elements that our office owned and did the engineering kind of breakdown for. So that image that we were looking at earlier was kind of in the upper left-hand corner. That is the kind of main segment we were first looking into earlier. And then this is kind of a model, just to spin around so you can start to understand the scope and size of this building. So like I said, we do everything, kind of all of our modeling is all driven through Rhino and Grasshopper. So these are some of the elements that kind of make up the house that we own, and they're all highlighted based off of the individual uses. And that kind of scale figure is put in there to understand the scale and kind of real like heft of this entire building. I think we're frozen. Awesome. Let's see if I can get to the next slide. So see, these are some drawings that our office does to kind of understand the scale. So each one of these form systems, which is labeled using a numerical system, which is a standard practice for our office in particular, to try to remove language, to make everything very simplistic in the way that it's understood on a site, whether it's understood on a shop floor, all the way through the engineering process, by kind of continuing the way we look at it is, if we're going to use data to build and engineer the elements, we're going to use data to deliver it to the site as well. So each one of those elements is about 4 foot by 8 feet. So this one particular column is roughly 48 feet tall. You can see all the different segments that are used to create each one of these form systems. And these form systems are all generated out of Grasshopper. So we generate automation tools to be able to do this, where you can input a single surface into the geometry, and it can output what we call a cassette for the formwork, which is all based off of structural parameters to include the depth, the thickness, the spacing of the ribs, as well as the liner face on each one. So you can see some images from the process of fabrication in our facility in New Hampshire. Each one of the parts is named, again, using that very similar kind of numerical coding system. And then a few of this assembled elements that are both a mix of plywood to get the appearance of kind of a wood board form onto the concrete itself, as well as a mixture of MDF surfaces, where in double curvature areas, the design team was very adamant about having zero board form texture onto it to delineate the differences in geometries at the appearance. And then you can see some images of our form systems being integrated into the concrete prior to them being peeled away. And some more to start to understand kind of the scale and magnitude of this project. And then the next couple images are more recent. So like I said, it's currently under construction. They just recently finished the last casts of concrete over the past 3 months. Our team is now actually working to develop the interior elements with them as well. They have some complex thermoformed Corian pieces, as well as some more interior concrete pieces and woodwork as well, to kind of under some more images of the space. We kind of joke in our office that this thing is the Millennium Falcon. It very much is this like Star Wars-esque plan geometry for the building. But there's some really beautiful moments inside of it, I think, that are really kind of highlighted as with these perspective views through the space that, you know, are both interior but also exterior, and kind of gazing out in the courtyards, I think are really interesting. Finally, this last project I'm going to show is the Alliance Theater Transformation Project, designed by Trahan Architects. This project I worked on for the past 3 years. It completed in February of this year, and unfortunately has only been able to hold about 2 performances in the space to date, due to the COVID-19 pandemic. So these are some images of those performances very early. Our office was contracted to do a design assist and understand the geometric complexities of the entire theater. And we also fabricated every single one of the interior wood panels that you see in this image. They're a mixture of wall panels that are driven off of acoustic performance. They're also a series of guardrails, what are going to be referred to as components, which are steam bent elements, as well as the ceiling. Overall, there's about 270,000 linear feet of white oak in this theater, and each one of those pieces is a 1/2 inch by 1/2 inch strand that is intended to be continuous, wrapping from the stage all the way around the theater. So the components kind of form themselves around the balcony and kind of bring you into the theater, and then the roof kind of creates this porous area to expose the kind of theatrical spaces up for where the catwalks are, and then everything else kind of wraps around to really draw the audience to the stage. Some of the forms are very, very dramatic. They're really, really beautiful. It was kind of unbelievable to see some of these elements, which the longest one down in the bottom and kind of the center right of the screen, which is referred to as component 1 at the stage, was about 28.5 feet long as a single panel. It's about 6.5 feet tall as well. So if you actually stand kind of at this moment right in the center of it, closest to the stage, where it almost creates this inflection in, it actually is about 8.5 feet tall at that single moment. So you become completely engulfed inside of one of those elements. So the design team, Trahan Architects, had worked in this theater. It's a renovation. The standard idea of this project was that it was kind of this box, and it was how you could break the original box of the theater that was built in the 60s and kind of transform it into wrapping itself from the stage and then all the way around the theater, and how you could start to be playful with the individual moments of the lines of the theater to create swooping spaces for both occupancy, but also for acoustic performance. So every one of the surfaces is highly designed towards the acoustic performance of the theater, to be an optimal Broadway presentation. So this is a section through the building, so you can see it's kind of very standard in its original box. And then this shell of the interior really kind of morphs itself to the inside of the theater as being extremely dramatic. The design team, when they were working, is very oriented towards ideas of making and towards crafts. So a series of these are actual mock-ups that were made from the artist Matthias Pliesnig, who is out of Brooklyn, New York, to kind of make some elements to understand the geometries and understand how they could actually be formed, created, and built. And these were all built during the initial design phase, during schematic design. These weren't for the actual theater themselves. These are very early on prototypes showing the balcony face and the way that each one of the layers would get laminated together as an individual strand, as well as trying to look at ideas of what a stair looks like on the left-hand side is kind of a balcony face, and how the stringers, which are the kind of strands of wood referred to in this project, and how they integrate into the stairs, and the geometry starts that's parallel to the floor, and then how it can morph itself into more of the organic geometries. And even areas where the stringers would be open and then they would close themselves to the cap, and then the cap would be fabricated out of what were called pie wedges that could be morphed all the way around to make its closing over and then opening itself back up on the opposite side, since each one of these elements is kind of dual-sided. And then on the right, you can see that image is actually a Z-shaped profile to create a reflective property for an acoustic performance. So each one of these elements is acoustically driven to either be open to allow sound through it, or it's diffusive, or it's completely solid and closed and it's a completely reflective surface. So at the onset of the project, we received this as a surface geometry model to just understand all of the elements. What our team does to work with the architects would be to refine all of the geometries to make them a little bit smoother, to help them identify the areas. And then even you can start to see the breakdown of elements in panelization of how you could streamline many of these elements for fabrication, as well as ensuring that there was a centerline datum through the theater that you could create a mirror, because you could reduce the amount of manufacturing time when it can be done as a mirror for itself. It also ensures the ability to create better streamlined layout when you could check like the north to the south side versus everything being completely unique. Our team then spent about 6.5 months designing every single one of the locations of the stringers. So each one of the stringer locations was based off of a written specification of how the acoustic performance needed to fit. And then our team wrote Grasshopper scripts to lay out the stringers on every single one of these. For us, we needed to start with a workflow, because for a project of this scale, you had to get to a point of how do you translate these complex geometries into physical elements. So we needed to be able to track and check ourselves the entire time through where the stringers were. So this was a very important exercise for our team to not only understand all of the nuances, to understand the linear footage of all the material that's required, but also to work with the design team directly to lay out the stringers in ways that which our team as the fabricator could understand exactly how the material is going to behave, which is very critical. If you don't understand the material that you're designing with, many times it could get removed, or it's almost impossible or too expensive to build. This is a rendering of the theater that you could see. Once we were able to translate all of the stringer geometry back to the team, they could integrate it into visualizations for their office as well to sell to the client. And then from our team's point, it was time to start breaking this thing apart. How do you start to panelize all of these elements to be built and fabricated? How do you start to delineate the difference between wall and ceiling, or component and ceiling as well? Since each one of these surfaces wraps itself all the way around the theater, how do you get 270,000 linear feet of oak to appear continuous and never end? So these are some of the Grasshopper scripts that were used to generate the stringer spacing for the component based. And this was sitting in a series of meetings and kind of in a virtual world. The architecture team was in New York, Chicago, and New Orleans at the time, to understand what the parameters were. There was ideas about what the vertical rib needed to be for the spacing based off structural as well as acoustic performance, how there was these hip lines inside of each one of the forms that you could then trace the spacing into to create gradient spacing, and then run the stringers across where all of the rules. So each one of these scripts integrate with themselves to ultimately create these forms. And for our team, this workflow was very critical to always use the finished surface to then derive and use planes as a fabrication technology in terms of fabrication to ensure things are planar and true that you can test later on, as well as the stringer center lines themselves to be able to map them through the process. So these are some of the components that are then actually in Grasshopper. They were all completely modeled inside. So you can see this was a video. I'm not sure if it's going to work correctly, which I apologize for, but essentially every single one of the elements is completely modeled all the way down to every single individual bolt. One of the most critical aspects was the workflow that we developed. I mentioned using planes and the surface and the stringer center lines. So now it's the idea of the next part of this where I'm going to talk to is how do we actually build these elements? So the first was we created a jig system which was standardized to every one of the components. They were all unique in their geometries, to a base plate with a series of steel posts, and then automating a process where a series of boxes that could get created to hold each one of the elements in place. The next was a series of inserts of plywood that would go in to act as the rib. So the plywood is being utilized because we needed a planar element. So it goes back to the rib. So every single one of those, which is then machined in a 5-axis operation, allows us to create the different angle and not only in plane, but also in elevation for every one of the ribs for them to be formed against. Then a secondary piece is placed on the front because every one of the ribs is completely unique. And instead of machining them, we steam bent each one in individual layers of 1/4-inch material. The reason this had to be done was as these swooping stringers are going across the face, you can imagine that the perpendicular moment for a glue surface to map on something that's moving in space needed to reflect to that. So each one of these ribs are actually twisting in space as they go down, not as dramatically as I kind of just gestured, but to be the exact kind of normal to the surface at the moment that the stringer intersects with the rib, so you can ensure the most glue space possible onto the actual element itself. So that even all the way down to the moment at which two materials touch each other is considered in the way that we're crafting this type of information. Because all of this is being done by hand, none of this was done with the machine. So we have to embed this logic into the actual parts themselves. At which point the stringers could all be steam bent and run across the faces of every single one of the ribs and created as an entire element. It could then be ejected from the mold. It could be sent to finish. And then the other one, the inside was built on an exact replica of the other form, but it's now just the interior face. So we could ensure that the two faces would line up. Once the two forms were ejected from their jigs, we would dry fit them all together to ensure that they would fit in our facility. So these are some images of the craftsmen actually steam bending and clamping each one of these pieces. Like I mentioned, these are all done by hand in the way. Each one of these is located in space because, again, they come back to an acoustic performance standpoint. And the center line was asking us, how do you translate where each one of these goes into in space? So the system we used was a series of tick marks on each one of the ribs that was actually done with a pencil. But as you can see, there's those little tiny green dashes that are there, which I'll get to, but we created a workflow using aerospace technology to use a 3D laser projection system that could translate the actual BIM data directly into the physical space by projecting it onto the geometry. So these are some images more of those elements being fabricated in our facility in Colorado, in New Hampshire, actually. And the one in the center here is actually that first component I'd mentioned that's about 27.5 feet long. So that one is about 8 feet tall to understand the scale of standing in that moment. Each one of these was clamped on with an individual element and then removed. So each one of these stringers is a glue joint and only a few pins in some locations based off of the fabrication strategy. So there's really no fasteners that are visible throughout this entire theater. And you can see one of them in our finished booth getting ready to be finished, as well as some of the kind of moments at some of the bigger components. And these images here are some images of some of the ceiling panels and what was referred to as the knuckles of the theater, which were the moments kind of right at the ends where the large swooping ceiling would go and wrap around the catwalks. You can see the panel on the left for the image is sitting on the bed of our CNC machine. We have a 25-foot by 10-foot by 6-foot Z CNC machine in our facility that can do 5-axis operation. So that panel weighs about 2.5 tons that's sitting on top of our machine, to think about the scale of these things. So one was about 28.5 feet long. And then we developed a strategy where we created these custom molded profiles of the wood that you can see on the right, where it has this small rounded back profile, where during the CNC machining of every one of the panels, we would actually use an end mill ball cutter to actually route into the panel the exact path for every one of the stringers to be located. So you could ensure the exact location, and that from one panel to the next, every one of them would align with the use of a comb at the end to replicate where the seams were. And that was how we were able to build these massive elements over the course of 1.5 years, while some of them were already installed in the theater. For our office, the big question and kind of a big part of my individual practice is, how do you get to the digital world into the physical world? There's kind of this feedback loop that persists through CAD and BIM, but there's a lot of errors with it, where there's a lot of overlap, there's lost information, and there's a lot of error stacking that goes on in between each one of these that we started to identify in the complex fabrication world. So at our office, we've started to introduce the idea of reality capture and 3D laser projection and integrating augmented reality workflows into our fabrication process as well as our design process. So in this case, we realized that we could project the stringer center lines that we originally mapped in 2018 at the onset of design assist for this project onto the stringers while they were being fabricated in the fall of 2019 in a totally different way. We could use this geometry to project areas where light fixtures and handrails would start to get cut into the stringers. So we could project based off of where an electrician had placed one of his lights in the BIM model and project it directly onto the face of the stringers with a 1/132nd of an inch tolerance, which is about 60 times better than what the construction industry works to today. So it's kind of a revolutionary workflow. So we would check not only the edges of the jigs to make sure that every one of the parts was located correctly, but we would also check the location of every one of the stringers to ensure that they're right. So you can see that even though every one of the stringers was built by hand and formed by a craftsman and not done by a machine, we're able to get to the stringer center line to be within, in most cases, a 32nd of an inch to a 16th at worst for every one of these locations for all 200,000 linear feet. For us, the question is how do you start to use this technology onto a site? How do you bring this into the digital world to start actually laying out the location of every one of these elements? We start with using a laser scanner to kind of project in the space. And you can see in these images that there is a robot kind of doing this. This is part of our research and development initiatives that we were doing at the Pier 9 Autodesk base in San Francisco, where we've been looking at ideas of how you can deploy a 7-axis robot onto a site at a stationary point to do capture and layout for the entire building system all the way throughout. So you'd first laser scan the space based off of the series of targets. And then once you have that in its most simplest form, you could then project back onto the geometry by extracting that information. This works really simple in kind of a cube or a traditional space, but how can you start to understand complex geometries? And the use of this tool can no longer be done on just planar surfaces, but we also have the ability to project 3-dimensional geometry as well. So you could build, in essence, a box as an original room. So as an architect, you can design these very simplistic spaces that are built towards traditional construction, that are built towards framing of walls or masonry and CMU and the traditional elements of construction. But then you can allow the complexity to exist inside of the finishes or the millwork. You can exist and create these very eccentric spaces that are highly designed that you can check at a very high tolerance through the use of this technology, but allow the craftsmen of construction to be doing it in the simplest way that they understand, since they work at different tolerances, and allow a more manufactured space with highly complex capabilities to really take in all the complexity. And you could then project back into space to check every one of the edges in 3 dimensions to really start to bring the digital world into the physical world. And then we can go back and laser scan to make sure that everything is in the exact same spot as it is after. So this was a workflow that we developed and we piloted on the Alliance Theater project that won us the R&D Award Platinum from for a couple from the AIA in 2019 for all of our R&D initiatives, where we would laser scan the space and turn them into 3-dimensional mesh models, which we could overlay all of the parametric models that we had generated for fabrication for every one of the elements, where we could check each one of the elements that they're going against. In this case, you're seeing an image of where the balcony component is wrapping. And you can see the concrete below is creating a 4.5-inch hole because the concrete was out of tolerance. So we have the ability to get in front of every one of these trades before our work goes in to help the contractor understand exactly how they can fix all this stuff. And we even recommend ideas at how we could build our own form systems that match the geometries versus the existing geometry, since we have the use of reality capture. At which point, for our team, we actually went onto the site and we would deploy the 3D laser projection system onto the walls and the floors to lay out every single one of the components throughout the entire space. So we were doing this as a team to kind of check everything, but also to get in front of our install team so they didn't have to use any paper on the job site. Everything was completely digital. And then here are some images of the early days of install. So I was actually on site the day that this component got hoisted into place. And I can tell you, I've never had anything close to a heart attack, except for on that day of watching this 28.5-foot long piece of millwork that I've spent 2.5 years designing just fly overhead on a series of ropes that are used for climbing, because it was all they could use to fit in between each one of the stringer spaces. And then here are some images of the theater today once it was finished in February of 2019. So some of the balcony spaces and how the wall panels kind of wrap down and separate from the ceiling, and then they join themselves back at the stage. So this was one of the early performances again, as well as another image of one of the performances in the space. Um, so that's kind of my presentation of at least some of the work that I've been working on over the past couple of years. So yeah, I mean, if you guys, I don't know if you guys have any questions or kind of want to take it away. I'm sure there's tons of information to unpack there, kind of in this different world of complexity and fabrication that I exist inside of.
To me, that was just like amazing to see like how far kind of fabrication has gone. Like the Alliance Theater just reminds me of was it the Zaha Hadid project in Azerbaijan?
Yeah.
I think it's really amazing how much computer animated design or computer aided design has enabled architects to design really whatever they imagine now. And it's just a matter of figuring out how to build it. And I think it's really interesting how there are companies or firms like yours, CW Keller, that can actually kind of materialize our dreams.
Exactly. I mean, and that's kind of it. I mean, that's, if, a designer, any of you could create anything inside of the kind of the computer world at this point. There are endless tools to do it, but we're still using the same tools that we've been using for, the past 100 years in a wood shop to be able to make it. So the question is, where do you identify the complexity? Where do you identify the challenges in order to build it? And then it's finding, firms that are willing to take on those challenges and say no, instead of, being the general contractor. Many of you may have experienced this inside of a co-op, that something gets VE'd or removed from a project because someone doesn't understand it. And it's our job to bring the awareness, bring the idea of how it can be built so it doesn't get removed, but how do you refine something to fully make it kind of a reality?
I think that's really interesting. I think like one question I have for you is kind of how do you think we can bring this kind of technology to kind of the broader public or like a general audience to kind of use these technologies that we've had? And I think they're kind of like developing at a rapid pace now. Because I think I read probably over the summer something about kind of collage and assemblage in the 1960s as kind of an outpouring of uh, people or architects themselves not having the kind of the craft anymore because they're assembling these buildings out of prefabricated pieces designed not by architects but by contractors in the field who some might say are just kind of lazy and want to simplify things to a poor person's Miesian kind of kit of parts. But I think with kind of like tools like Rhino and Grasshopper, I think now we have kind of this imagination. How do we actually kind of create a system for kind of the general contractor to build what we want them to?
Yeah. I mean, the unfortunate part of, that in my kind of opinion, the reason why I kind of ventured into an alternate practice and not traditional architecture, is because I think that that onus actually falls onto the designer itself. It doesn't fall onto the general contractor. I think a lot of the mistakes that are made in the design process is that these tools are so readily available to create anything and design anything, that so many designers don't fully build things to understand the materiality of exactly what they're designing. Instead, they come up with a form or a shape that they're drawn to based off of visual ideas, that that really are kind of aren't embedded in the material, the actual making of something. Um, so from that point, if for instance, if you design, something and it's really needs to be done with like a steam bent wood, or, if you want a monolithic form that doesn't have joints inside of it, you need to go to like a Corian or a thermoformed material. But an architect may say, no, I want that out of wood. And it's like, sorry, you can't do that because wood is a living and breathing material. It's going to expand, it's going to contract. You cannot create monolith with it. So it falls back on the architect, I think, and the designer to really understand the material. One of the worst things I ever heard, and what kind of really forced me into um, really get into this type of work, is I was on the phone with a designer one time, for a project, and we were doing like more steam bent wood projects. And the designer had said to me, well, I've been able to make it in a Rhino model. If I can make it in a Rhino model, you can make it in real life. And that's just not true. It's, yeah, we can make anything, you know what I mean? But if you don't think about the material of it and you don't think about how that material behaves, then you can't get there. So, you know, that may be a kind of like a partial way to your original question, Matthew. I think the other part of it too is it's about communication. You know, I think there's an idea of craft that, I look at architects kind of, especially during the modernist era, that were delivered by this idea that you had to be an apprentice and work for 5 years and understand this craft and become perfect inside of it. And we went away for that for so long, especially kind of during this postmodern era. And then all of a sudden we hit computer and it was like, we can make anything. Let's just become generalists and go back to everything. And now all of these like designers are coming up with these crazy things, but they don't understand how to build them. So that information cannot be communicated clearly through drawing because it's more expressed through form. Those types of ideas aren't being expressed through tectonic. And I think that's where a portion of it comes back to. And really why I think a large portion of it too has to fall back on the designer is that's when the original conception of the idea is made. Right now in kind of the United States especially, but even in the world, craftsmen don't exist anymore. Trades are a falling thing away. So if you can have the ability to find the complexity of an alliance theater where it can be done through, augmented reality and specialized fabricators that have the ability to do it, but then a construction company or a general contractor on site, all they have to do is build a box. A box is easy. You don't have to train anybody to do that. You don't need specialized craftsmen to do that. That all the kind of money, the time, and the expense and the complexity can be placed in one area. So it's like picking your areas and being able as a designer to identify that. Like one of the hardest things we had in the Alliance Theater project was there are areas where the walls were supposed to be framed to follow the exact geometry of the wall panels. It's why? Like, why do that? Why not let the wall panel be its own thing separate from the wall? They don't need to follow each other. Everything doesn't need to be like an offset of an individual surface. Things have material and depth and layers to them in order to build. So that's kind of where I see it. And that's really the only way to kind of make it readily available. I think there are hundreds and thousands of companies and people have CNC machines at this point in their home, but if you don't know how to use them or design things to be made on them properly, we're just kind of be stagnant in the kind of current system that we're under.
Yeah, it kind of reminds me of the kind of the traditional architecture before probably like the 19th century, where the architect was really the craftsman. He or she knew everything about how to construct kind of the cathedral, the building that they're designing. They're as much the craftsman as they are the architect. And I think today, there are a few firms like yours, and I think Nada with NAD Lab, that's a really good example of kind of the architects going back to the craft. But I think it's still really hard for us to go back to that once we've kind of like resorted to the contractor to do the work for us. I think it's interesting, but I think I'll open up the conversation to everyone else if they have questions or comments.
Yeah, so I have a question about like the actual individual pieces that like were designed for like, the different spots around the theater. Were they like designed specifically for like acoustical reasons, or was it for, I don't know, like, I mean, it could be for airflow, but or for like user organization or something? Like, was there like a strategy behind like the form design?
So the answer is yes and no. There are certain areas in the theater, and the stringer spacing is very, very specific to the acoustic performance. For example, on the ceiling, those panels are all reflective material. So the design criteria on that was the stringers could never get closer to each other than they are deep. So if they're, for instance, if they're a 1/4 inch like thick or tall, they could never get closer to each other than a 1/4 inch, but you could spread them out as far as possible, as long as there was a substrate a 1/4 inch back as wide. So like that rule, for instance, for us on the ceiling, the design team came back and said, we need to pull $20,000 out of the material. So my team sat down and we looked at that, one day and said, well, we can exploit this right here. What if you make the stringers of the ceiling get wider, and we were able to pull $25,000 worth of raw material out of it by bringing the stringer spacer apart? So they get closer at really tight areas, and then when the panels get wider, they'll open back up. And that's all based off acoustic performance, but that's also to allow not only an aesthetic from these kind of like really dramatic moments where tightness and openness, as well as just kind of general cost to save money. On the components, there are areas where the way that they're crafted is that at the ends of the stringers, or at the ends of the components, the stringers are exactly an 1/8 inch apart. So they seem really closed. And the same number of stringers needs to go through the entire thing. So at one end, it may be 42 inches tall, and at the other end, it may be 54. So you have them go through that space, and then in the middle where the hip is, it may be like 120 inches tall. So you start to get these open and closed spaces that were then designed at that point was a visual aspect. How far can we make these things open to be dramatic? But we also don't want somebody to be able to stick their hand and drop a program through the center of one of these, because we'll never get it out. So there's like all that type of like playfulness that was inside of it. But there are many moments, specifically in the wall panels and the ceiling panels, that are acoustic. There's some moments in the component scope that are acoustic, but the rest of the components are much more visual to be as dramatic as possible in their appearance as well as their form.
I have a question. This is regards to sort of career and practice and what you were taught in school. Obviously, like you didn't go through like the conventional sort of route in terms of career, and I want to know what that was like in terms of perspective. And you would tell us like through class and now how there would be these ambitious goals from architects, and how does that sort of translate on your practice and just personal sort of approach to that?
Yeah, so I've always loved making, and I love architecture. I'm like drawn to it spatially. I think it's one of the most like compelling at a psychological level, like in the world. It's so interesting to me. And I'm a maker at heart. I've been doing woodworking and making things since I was like 8 years old. I built my first house in like a building trades class when I was a freshman in high school. Was kind of the first time I ever really like framed a house. And then obviously went to architecture school, and I like didn't really know what I was getting myself into. And then I like was just like, oh, we're just going to design, like many of you probably when you're a freshman, or if you currently are a freshman. It's just like, oh, we're just going to draw houses, and like that's it. And there's really not much to it. And then I had a couple of professors that were really got into kind of ideas of concept and the poetry that can exist in architecture. And I started reading a lot of theory, and I got engulfed in the world of Peter Zumthor, who's my favorite architect, and reading Thinking Architecture and talking about materiality. And then I started to just kind of go into this whole other world. And then all of a sudden I was like, oh, wait, there's a fabrication shop at Wentworth. And I became really close friends with the person who was running it at the time, this guy named Alex Cabral, who's now at the University of North Carolina, Charlotte. And just started testing with a CNC machine, starting to make all sorts of things and try to understand, every move that I made in architecture, I felt was very understood, and what it meant from both material and craft. And I became just fascinated by those ideas. Still no idea. I thought I was always still, when I was going through architecture school, was going to work in general practices. I did all of my co-ops at architecture firms. I did all of them. And then when I got to thesis, everyone thought I was going to do something on making and woodworking. And instead I just completely said no. And I did something on landscape architecture. And it was because I was fascinated with this idea of interdisciplinary practice and how landscape architecture was interesting to me, but not from its landscape perspective, but how you can understand elements in landscape that can be used as architectural elements. So there's like this interesting irony that you start to like use elements as one or the other that start to define the difference between, we have to start to question whether things are interior or exterior, where it's architecture or landscape. And that like ventured me into this whole world where I was like, architecture doesn't need to be traditional architecture. So then I was coming out of school and I got an opportunity. Somebody said to me, hey, do you want to go work for this wood shop? And they're doing really amazing work. And I saw pictures of it and I was like, oh, this is cool. And I had offers to go to like traditional architecture practice, go back to where I did my co-ops. And I went in for an interview at CW Keller. And I love telling the story because it took me about 5 minutes to realize I wanted to work there. And it was, they took me down, they showed me a whole bunch of stuff. They showed me the Alliance Theater project and renderings, and I had seen it on Arc Daily as an architect student. And I was like, wow, this is cool. I had no idea we were going to work on it. At that point, we were bidding it. And there was one man down on our shop floor, and he was on his hands and knees with a piece of plywood with screws sticking out of it. OSHA would be having a fit. It looked so dangerous. And he had a stack of 1/2-inch pieces of wood that were 10 feet long. And each one of the screws was placed at a different radius around this board, all the way from a foot to 10 feet. And he was bending the piece of wood on the screws and holding it in place and just writing on a Post-it note whether or not the wood was going to break or whether or not it would bend to that form. And I asked them, I was like, what are you doing? And they're like, we need to understand, in order to build and manufacture this, the moments at which the material is going to break, at which point we have to say we need to machine it, whether it needs to be steam bent or whether we can do this by hand. And then after they found out where that line was, they would then bend all of them and screw them to a board and hope that the force that compounded as you screwed more and more stringers to a board, that it didn't deflect and spring back and it wanted to go from curved and just straighten out. And I was like there for an hour watching this and I was like, holy shit. I was like, if you're going to like care this much and understand a material like to this high degree, like this is this interdisciplinary practice of being able to look at material from a totally different side of architecture and try to communicate back to the architecture world. And really, I find more of myself trying to now work with students, to now work with architects, to teach them how to detail for material, of how can you get these ideas of craft. And that's where I find my most fulfillment isn't in like designing and then like finding out what screw size goes into a bolt, but it's like being able to like translate and really get to the ideas of interdisciplinary practice of people that, you know, if a designer wants to come and they want to design that thing in Rhino and say, I built it in Rhino, now you can make it. I want to teach them to go make it themselves and go figure it out and find the failures, because that is the best way to learn, is kind of doing it that way. So I always kind of approach things from a very different side, in that idea of making craft for me is like everything that I do. I love to be a very hands-on person in making things. And that's kind of how it got me into a totally different design practice. And I don't ever see myself working inside of a traditional architecture firm. I just can't. Like, I'll always be an outsider looking in, but trying to always give the design and architecture perspective to everything that I apply to, and trying to be a specialist in so many things, to ultimately be an architect. And yet I still consider myself an architect. Like, I don't consider myself a fabricator. I don't consider myself an engineer. I consider myself an architect that's working at an engineering company.
So then I have another question regarding your career then. So last week we had Jennifer Gogler, and she came and sort of talked to us about her career. Like, she started with like an architecture degree, and then she worked for a while, and then she realized she had an interest in academia. Mm-hmm. So, I mean, we are aware of like her story and her path. So I'm curious as to like what yours was, like on how, like, you know, you graduated and then you worked for a while, and sort of how you got into, you know, teaching.
Okay, yeah. So I've kind of, ever since I left school, I've always been semi-involved with academia. You know, the person I mentioned earlier, Alex Cabral, who works at the University of North Carolina, Charlotte, after I met him in the shop, he became like my best friend. And I go down to like North Carolina like 4 times a year, and I just go into his facility at North Carolina because they have 7-axis robots. And at the time when I graduated, Wentworth didn't have one. I spent like 3 years helping like Rob and Chris write the proposal for us to get one, and working with Kelly. And then they all of a sudden one day the robot showed up as I was like getting handed my diploma, and they were like, thanks for coming. So I like started going to North Carolina, and I was just like involved with students and involved with that idea of making. And I think that there's something so free in kind of the student aspect of curiosity, that I just couldn't escape it. So then after I was out of school for about a year, I started teaching with Rob, and coming in to help him with his studios of like making. Like, we were doing carbon fiber and robotic stuff and going everywhere. And I was begging the school to let me teach. And they were like, no, you can't teach. Like, you've been out of school for like a year. Like, you don't know anything. And then I kind of, a couple of years went by, and then I was doing reviews with Rob and teaching with Rob. And then I met Mark Mulligan. And then they kind of like dropped me in and they were like, all right, we want you to come teach. And that was kind of it. And I was like, finally, yes. Because for me, teaching, like, I kind of, as a leader in my office, I'm able to help people teach and understand the kind of technical side of things. But students, you can get more like the fundamental basis of like, the foundation of the principles of kind of design and what making is, at least in my ideas, and the importance of what craft is. And I think is so valuable to all students. And quite frankly, it's an escape for me to be able to kind of get away from work and the real like nitty gritty where you have to sit in a meeting of, how are we going to detail this door and where its hinges are going to go in order to work, because it's an 870-pound door that's 14 and a half feet tall. Like, that's, after like 2 hours, that conversation gets really boring to me. And I'm like, all right, let's go 3D print some clay and find out like what the gravitational shift on this, so we can try to create like a formal pattern. And I have no idea if like clay extruding architecture is ever going to be a thing. This is really fun. Let's make some ceramics. So that's kind of, it's like an escape for me in that way. And that's how I kind of got involved. And it's kind of something that I've wanted to always have, this like dual portion of practice and academia as well, as an ability and escape to kind of research and try new things.
Does anyone have any other questions? If not, I think the team has made up a couple questions. Okay, I think this one's a good one. So at what point does kind of the craft become theoretical or spiritual to you? Sam, do you want to elaborate on that question? Did you write that one?
I didn't write it, but I can try and elaborate on it. I think, let's see. That's a good question, actually. I think it's kind of wraps back into like my question earlier about like the whole form, like the different forms in the theater. Kind of like, I think your answer was more like theoretical. But then I guess, is there a way, or like, are you working on like a project right now that uses craft more spiritually than it does theoretically? Maybe.
I don't think there's really nothing that I think that is nothing that I'm like working on right now. I think to kind of answer that idea, theoretical idea of craft versus kind of the spiritual. I mean, I think the theoretical idea of craft is very much applied to me during the actual design process. I think craft is a very specific word that gets at a certain level of detail and understanding of something. It's beyond just kind of making. That being able to fully understand something, I think, is like a really important idea. The word that I became fascinated when I was in undergrad, and I use all the time, and it's become my favorite word, is holistic. I think it's the understanding of everything. And for me, craft is the holistic example. Holistic applies to everything, but craft applies to me of the entire process. I think it's above kind of being holistic. So in that sense, that's kind of the theoretical aspect of it that I approach it towards, that craft starts at the original idea. It isn't introduced at the actual making process itself, but it's thinking about every single move that's being made. It's a strategic thinking. For Angelica and Sam on like the studio projects, it's thinking about like, when you design a component, what does that mean? Or, in that terms, like, how big are you making things relates, and everything has a relationship to each other. And that when you make one move, what does that mean for the next? It may mean that there's something, that's affected, or it's kind of better or worse for each thing. And then it's a decision of whether it is kind of or not. And that's where craft is through the entire design process. It's not just designing something and then coming back to the end and being like, how are we going to build it? It's knowing that in the process. Then the kind of the spiritual side, I say, of craft is for me more when it starts to translate outside of architecture and kind of comes into like everyday life. If like for me personally, like I love to cook, like I love food. So like it's like the scientific thing for me where like I don't even care about what the food tastes like at the end, but I just love the process of like making it and like not writing down like a recipe or anything. And it becomes like the craft and the process that it takes to make it, and it's authentic. It's the same thing for me. Like I got involved in, because I hang out with Rob way too much, of like starting to do like art and like painting, of this like real idea of process art, and got like super involved with like Richard Serra and like James Turrell work. I think is just absolutely unbelievably breathtaking. That then goes into the craft of how you actually make it and not caring about what the result is. It's the same thing that you can apply to art, that you can start to apply to cooking, but then you can apply it to design process as well, and kind of architecture. That this idea of craft can kind of translate through everything that you do in a way that you go about life. And it's not just about the design process anymore. It's kind of a way of thinking. It's kind of a way of being. That's kind of probably the more spiritual side of where I see ideas of craft.
I think that's really interesting. Like this idea of like craft going beyond architecture and like going into cooking or something. Because for V10, we had interviewed an old faculty member, Elizabeth Ghislaine, and she had talked about something similar where her passion for architecture kind of evolved into passions of other kinds. I think she also had mentioned cooking too. But do you think kind of in our education, do you think we silo ourselves into kind of this traditional form of practice that like you're creating a building and that's what you're always going to do? It's not very plastic. But do you think in our education, it would be more effective if we kind of use those kind of theoretical understandings of what craft is, what play is, what space is, and kind of base our education around kind of non-conforming architectural things and making them architectural in a sense?
I think it's a good question. I think there's something, like for me personally, like I said, when I first got to architecture school and I started undergrad, I thought architecture was it wasn't plastic. It was just buildings, but what I think about the beauty of that type of education in the way that the architecture kind of world, like an architecture education works, is that because architecture is kind of at the staple of it and it's kind of very traditional in that sense, it forces the idea of architecture becomes plastic in the idea of the designer, that they can interpret it themselves and find a way that they want to perceive and understand what architecture is. Is it about tectonic? Is it about space? Is it about material? And it lets them have a voice and understand exactly what type of designer they want to be. And you use architecture as a lens to understand that kind of it versus it being the product of it. And I think it's at that point when you can start to think about the architecture education that way. It's kind of the most interesting. For me, I look back at architecture and now like I sit here and, I went to, I did undergrad and then I went to graduate school. I was like, I'm going to get my professional degree so I can go get my architecture license and I'm going to become an architect. And then I didn't, and I have no aspiration to ever do it. And I'm like, why the hell did I go to grad school to do that? But it's like now in like retrospect, I look back and I can say the most important aspect of architecture school to me is a critical thinking process about thinking about an idea of like space or building and really critically thinking about everything. And it is the most unique and kind of intense way of problem solving you can do. And it's when you can start to look at architecture school as a way of problem solving and critical thinking versus it just being about the building. I think it's when you get to those tangible or ideas that it starts to get away from kind of the general practice. That might be kind of I hope I answer your question in that way, because I think the way like architecture is taught is really good. I think if there's a way that like you try to come up with a random thing and then like try to prove yourself that it is architecture, it's like the inverse of what you're actually trying to achieve. It's like you can't, it's like trying to stuff a like, you know what I mean? Like you're trying to like, it's almost like you're trying to stuff a sausage. Like you're just trying to prove to yourself as like post rationalization that what I've done is architecture, instead of trying to say, what can architecture be? I think is the kind of the different aspect of it. You know, because I think architecture, you know, in the form of, you know, like I'll use an example of like a Richard Serra drawing, which I don't know if many of you have ever seen. I know probably you've seen a lot of his like massive like Corten steel sculptures, but to me, I think his most interesting work is actually his drawings. And I say that because his drawings are extremely large in their scale. He does paintings that are, you know, 10 feet long by like 8 feet tall, and they're all done with just a single unicolor form that are just black. So they have a very heavy appearance. But if you put one of those paintings or drawings into a massive room, like a gallery space, it completely spatially changes the room. So that painting as a flat, planar object on a wall becomes architecture for the way that it transforms space. I think that's really, really interesting to think about architecture that way than just trying to prove to like to try to say what I've done is architecture. So I think that's where I think that's where the current education system for architecture, I think, is really, really done well, because it forces students to look at it as a lens to learn through versus the product of.
Yeah, I think that's an interesting perspective. Because I think I agree that like the education shouldn't be forcing you to see something or see something as a product of as architecture. Uh, more along as seeing it through a specific lens.
Yeah, I think it's really important, like, to always be able to question what is architecture. You know, and that's kind of the thing. Like when I see people that go into like different practices, you know, like if it's like myself for into like fabrication, you know, I'd still consider it to be architecture because it's just me seeing it through like architecture through a different lens. Or, you know, sculpture is a form of architecture, painting is a form of architecture, and being able to question, is this architecture, I think is way better than trying to prove to yourself that it is. You know what I mean? I think it's a really different, it's just a mindset of the way that you approach it. You know, I'd rather be in the conversation to talk about why it is architecture or why it isn't architecture than to be that person that's there that's like, no, this is architecture, and like trying to tell you and prove it to you that it is.
Yeah, I feel like architecture, like the field of architecture, the discipline itself, is kind of a very kind of uh, individual kind of subset where we can see anything and say, oh, that's architecture. Like you see books on a bookshelf and you're like, oh, that's architecture, it's telling a narrative or something. And people come and ask you, you're like, what? And you're like, well, like the space and all of this, and it tells a story, and they just think you're cuckoo or something.
Yeah.
Because I don't think anyone who studies like economics and mathematics and is like, oh, this this drawer is mathematics, you can't, I don't think it applies.
Yeah, I think that's what makes architecture so interesting. I mean, because it really is like a conglomeration of like everything and like all of your surroundings, everything. Like architecture comes from everywhere. It's not like a single body thing. So like for a person that walks down the street and it's like there isn't architecture, and if you ask them why and they say because it's not a building, it's like, okay, then you don't know, like you don't understand exactly like that. Which I think is what makes it really interesting, where like you can't say that for other disciplines. Like you can say, like I'm trying to think, like if you're trying to say like something isn't food or not, like I guess, you know what I mean? Like it's pretty clear that like if it's edible or like it's not, like it's
Yeah,
very, like kind of one way or the other. I think, you know, engineering is that way. It either like fails or it doesn't. You know, finance is the same way. That puts architecture in like a league of its own that allows so much interpretation.
I think it's also interesting because like basic our whole environment, everything that like is like connected to our senses is could technically be architecture even beyond like our senses. Um, and I think it's interesting like when people say every person is an architect because like we exist. Um, and then you get faced with that question, like someone randomly asks you at like a at the Thanksgiving dinner or something, like, why'd you decide to go into architecture? And you're like, well, why didn't you? I think I don't know. It's the question that's always bugged me. Like, why didn't you go into architecture? Why didn't you learn to do this?
Yeah, I get like I have people ask me that all the time. It's like family that will be like, because they know that like I went to architecture school, and they're like, so what are you doing? And I'm like, oh, I work in like this fabrication company, and I do like design research for construction technology. And they're like, what the hell is that? Like, that's not architecture. And it's like, well, and it's like almost like it's hard to explain in that. But yeah, it's like I think it's what makes it so interesting that everybody in the architecture community has the ability to have their own voice. I think it's critical.
Well, does anyone have any other questions? So I think we're running out of time, but speak now or forever hold your rest. No? No? Um, well, I think I can speak for all of us that this was a really interesting talk. I'm glad that we've had such an amazing group of kind of faculty members and professors who have been willing to talk to us. And thank you for taking like the time out of your day to speak to some architecture geeks.
It's easy when you're an architecture geek yourself. So
Exactly. Well, if anyone has any other final words, I will let you speak. No? No, Sam? Are you sure, Sam? Are you sure you don't want to talk about the snafu earlier?
I'm okay. We can discuss it at our next board meeting. It'll be fine.
Okay. All
It
right.
doesn't leave this meeting.
Well, thank you everyone for coming tonight. And have a great rest of your evening. Thank you guys.
Thank
thanks
you.
everyone. It was a pleasure.